dynamics find basically from here all the way to here and up to the very opposite frames.
Good afternoon, everyone. Today we are very glad to introduce you the dynamics of a single rigid body. And we are Group E, and I'm Wang.
I'm Iman.
And I am Petrus.
Yeah. So now let me introduce you the dynamics of a single rigid body. And to study the single rigid body, it's better to study it in the inertial coordinate. So what's the inertial coordinate? So we all know the center of the mass. So we just put our body frame to the center of mass. And then we study the dynamics of the rigid body with that. So it's the most convenient way. And then in the body frame, we can easily write the force and moment. So in the force, we can see the orders and the central pedal terms. And in the moment, the term I want to mention is the, you can see the IB times the dot omega B. So what is the IB? So it's the rotational inertial matrix. So it characterizes the rotational property of our rigid body. So this is a 3x3 matrix, which is symmetric and positive definite. And with that, we can calculate the rotational kinetic energy of our rigid body. So now let's see the inertial matrix in more detail. So in general, the matrix is 3x3, but if we align our body frame to the principal axis of inertia, we can simplify the matrix to just 3 components. So in this form, it's very easy for us to calculate the inertia of the maximal and minimum inertia of this rigid body. And also, we can use the rotation relationship to transfer the inertial matrix to our principal inertial matrix. And so one famous theorem here is the Steiner theorem, and that can give us the inertial matrix between different line coordinates. And it is, we can treat it as the well-known parallel axis theorem, which we learned that before. So with the property of the inertial matrix, now we can use that to describe the dynamics of our rigid body. So here's the twist branch formulation, and we write the force and moment into the upper line in the matrix form. So here, for the first bracket, we can see we combine the inertial matrix and the mass into the spatial inertial matrix, GB. So with that, we can calculate the total energy and the spatial momentum. And another fancy term is this Lie bracket. So you can see the Lie bracket in very tedious form, but with that definition, we can write the dynamic equation of the single rigid body in just one equation. And that's the introduction. So let's see the example.
Okay, so me and Patrick will start our example for today. And I'm going to start with a simple model. As you can see, it's a hemisurface on the top and the cuboid at the bottom. And for this simple model, I will do a hand calculation for the both center mass and how do you find the inertia of this single rigid body. So here, we assume the radius of the hemisurface is 0.5 inch, and we assume the cuboid is 1 inch by 1 inch by 2 inch as the height. And we assume the mass for the hemisphere is 5 pounds and the cuboid is 10 pounds. After setting up all parameters, here on the left is how do you find the center mass of this single rigid body. To find the center of the mass, first you need to find the center mass of each part. So here we have 2 parts, and for the cuboid is just the middle of the cuboid, like the center part, and the hemisurface is actually r times 3/8, about the center of the flat plane. After you find each part, the center mass of each part, you can sum them and get to find the center mass of the whole rigid body, which you can say is the middle equation over there. And for this one, there's a tip, is all the x, which is the distance, they should all be the distance from the same the side that you picked. And here is the center mass for this rigid body. This slide, I'm going to talk about the inertia. To find inertia, because our model is a really normal geometry, so there are actually equations for both sides, like both parts. And the top are the inertia for the cuboid, and the bottom is the hemisurface. So to find the inertia, I give an example. Here is you first, the same thing, you need to find the inertia of each part, and by the equation on the right side, and then you sum them up. And that's how you hand calculate with the simple model. And here is our real example, the major example. It's a Lego astronaut. It's a Lego astronaut, and you can see it's way complex geometry here, and you probably don't want to calculate by hand because it's gonna be too much of mathematical calculation. So actually we put into SolidWorks, and there actually a really good property for SolidWorks that you can directly get the math properties for the whole thing. And you just need to go to evaluation and click the math property. And here you can see there's all the inertia, the mass over there about this model. And next, I'm gonna hand to Patrick.
So, Mr. Astronaut has met with a terrible fate. That's terrible fate. He has the misfortune of traveling along the x-axis at 1 millimeter per second, while also spinning at 1 radian per second along the z-axis. I know, too scary. And so, the first question we must ask of Mr. Astronaut, we must ask him, what is your spatial inertia matrix? Now, as I'm sure we all did in the quiz today, we know that the spatial inertial matrix is simply the inertia matrix multiplied by the identity matrix, and then you have the identity matrix times the mass in the lower right-hand corner. So something that I think is interesting about this matrix here is that the IB term is the only thing that's really going to change based on a change in reference frame. The m times I, that's going to be the same whether I am the astronaut himself or if I am far away from the astronaut. The m times I term is always going to be the same. And so we do a lot of writing down of the things that we got in SolidWorks. And it's not very interesting how I wrote that down. But what is more interesting is the question of what is the momentum of the astronaut? Well, I'm glad you asked. Because the momentum of the astronaut is simply the inertial matrix times the twist. GB times VB equals PB and J. It's not actually a J. And so we do the matrix multiplication using matrix math, and you get this answer right here, which, you know, it's numbers and they don't really mean all that much, but essentially this is the momentum of the astronaut in the body frame. And so now the astronaut must ask, what can I do to stop this terrible occurrence of me moving along the x-axis and rotating about the z-axis? Well, Mr. Astronaut, we must apply a force. For that is how you change your velocity. And so, how do you calculate that? Well, you take the inertial matrix and you multiply that by the change in velocity. And because we want to stop within 1 second, the change in velocity is simply going to be negative the velocity. And then after that, you take the ADVB, transpose it, momentum, and you do all the matrix math, and you get that answer there. It's matrix math, I can't make that interesting. But the important part is that after all of this, the astronaut's fate is better. He's happy, for he has successfully stopped. And now he's just floating in space. Yes?
And to summary, there is a classical formulation for the dynamics of physical rigid body. We use the Newton equation to get the expression of the moments and the forces expressed in frame rate, and thus we get the range. And we can also get the rotational kinetic energy like this. And the key point in this formulation is the calculation of the rotational inertial matrix. That is how to calculate IB. And if you write this formulation with the form of twist and range, we can get the twist range formulation. And we use the spatial inertial matrix GB in this form. And we can also get the kinetic energy using this using the twist B and GB. And if we want to express the dynamics in other frame, for example, you want to express it in frame A, we first calculate the GA, and then we use this formula to get the FA. And here are some tips for the diagonalization and calculation for IB. For example, if we want to get a diagonal inertial matrix like this, only the diagonal elements are non-zero. There are two methods. First, if the body is of uniform density and the shape is very simple, for example, if it's a cuboid, a cylinder, or a ellipsoid of high symmetry, we can directly select the axis of frame B to align with the principal axis for inertia, so that we can directly get a diagonal IB. But if the rigid body is of complex shape, we cannot directly get the IB. It doesn't matter. We can there exists the frame C rotated from B. That the inertial matrix expressed in C is diagonal. The rotation matrix from B to C, RBC, is correspond to the eigenvalue of IB. And if you want to calculate the IB for a rigid body, that is of component parts. For example, this body is composed of two parts. Then we first calculate IB for each part at its individual center of mass. For example, we first calculate IB1 for the part 1 and calculate IB2 for part 2 at its own center of mass. And then using the signal theorem, we express like this. We get the IQ1 and IQ2 expressed at the common frame, which locates at the center of the whole body center of mass. And then we
sum IQ1 and IQ2, sum them together to get the final IB for the total rigid body. And that's how we get the IB for a composite body. And once we calculate IB, it will be very easy to calculate the rest parts of dynamics. For example, it will be very easy to calculate the range, dynamic energy, and momentum. And that's all.
Yep. Any questions? No?
You did
Okay.
such a good job.
So we're gonna hand out the exercise.